How do you do, ladies and gentlemen, and boys and girls, and teachers, and mothers and fathers, and people and parents? I'm Julius Sumner Miller, and physics is my business. And before we go further, this is a program on extraordinarily cold stuff. Indeed, it is so cold that I have something going here that we must get a look at. I have a tea kettle with some stuff in it boiling on a cake of ice. Oh, look at that. And my tea kettle is whistling. Isn't that something? So, question, what's in that tea kettle? I'm going to tell you, liquid nitrogen. So, as a point of departure, consider the following. Oh, by the way, let's get a view of what I've written here. Heat the air by talking. I made a little calculation. Somebody remarked that I did a lot of talking and the air got hot. So I thought I'd make a calculation of the same. It turns out that ordinary talk, such as I'm doing here and now, develops about 100 ergs of energy per second. That turns out to be about 1/10 millionth of a watt. 1/10 millionth of a watt. So it turns out that if 400 million people talked at once, they could light a 40-watt lamp, which goes to show you how much energy really comes out of this mechanism called talking. But regarding my program, the drama of real cold stuff, I have made a note or two. If we had ice alone, as we have here, that's 0 degrees centigrade. If we had ice and salt, a mixture, the best we can get is minus 20 degrees centigrade for ice and salt. If we put dry ice, here it is right here, dry ice, that's solid CO2, with alcohol, a mixture of that, that would give us minus 78.5 degrees centigrade. So we're getting down in the world, you see. But what do I have here? I have some stuff called liquid nitrogen. Liquid nitrogen, and the temperature is minus 195 degrees centigrade. I tell you, people, that's real cold stuff, and I want to show you some dramatic experiments with it. First, here is a Frankfurter. Let me pour some of this stuff out so you'll see what it looks like. Watch it. Look at that. Look at the enormous vapor pressure. Vaporizes very quickly. I'm going to put a hot dog in here. Listen. Boiling very rapidly. Boiling, because the hot dog is so very hot for the stuff. Here I'm going to put an onion in. Now, you know, if I cut that onion at room temperature, the vapor pressure, it'll smell, what shall I say, beautifully. I'm going to chill it in here. Chill it in here. Or consider the following. I have here a lead spring. Now, you see how absolutely unflexible this lead spring is. Absolutely. No elasticity at all. I'm going to cool it in there. Listen, listen. Listen to it boil. Or consider a rubber ball. Watch. Rubber ball, fairly elastic. Fairly elastic, although rubber is inelastic. I'm going to put this rubber ball in there. Just let it cool off. Notice, making the stuff boil, increasing the vapor very, very much. Now, what do we wish to show? That the properties of things are enormously changed by reduction in pressure. Here is another beautiful illustration, while those other things are cooling off. By the way, notice again, my kettle is boiling on a cake of ice because the ice is hot for the stuff inside. And by the way, I invite your attention to the enormous frost gathered on this kettle. Why? Because the water vapor in this studio, in this classroom here, is very, very much, and it is condensing on that kettle. Here is a lead plate. Lead. Now, you know, if I wanted to make music, I wouldn't have a lead plate. But listen. Thud. Dead, dead, dead. I am going to cool it off at a very low temperature, and it will have a remarkable property. It will sing like a steel plate. Or consider the following: a balloon. I'm going to put a balloon in here. Cover that over. Let me get out my rubber ball. Watch. 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 I'm going to drop it on the floor in front. Watch it now. Watch it. There it is. There is that rubber ball. I want to do that again because that's a lot of fun. Oh. Now, give me your attention strictly. Here is that rubber balloon. Look at it. Look at it. Look at it. Look at it. The heat of my hand warming the gas, expanding the gas in the balloon. Now, why did the balloon get tiny, tiny, tiny? Because lower and lower temperature decreased the volume of the gas. This is Boyle's law. Now, let me go and fish out something. Notice, I dare not go in there with my bare hands. What did I put in there? Oh, there's the hot dog. Look at it. Look at it. That's the hot dog. Let me put a couple marshmallows in there. Let's get a few. Too bad to waste that, but it won't be wasted. I can eat it. The balloon again. Watch it. Very cold stuff. Now, what did I want to show you? Oh, the lead. The lead. Where did I put that? Oh, I guess I'm... Yeah, watch it. Watch it now. Watch it. Watch it. I'm going to put a weight on here. I'm going to put a weight on here. Notice. Notice. Notice how elastic it is. It has a little oscillation. I didn't cool it long enough. Now, where am I? Consider the following. I have here a copper tube and a steel tube. I have some liquid nitrogen in here. I'm going to submerge this system with a cork stopper into this Dewar flask, this thermos bottle. And what can I prove? Well, first you'll see an enormous stream of stuff emerge from here, but the water vapor will gather on here and freeze, and thus we can determine the thermal conductivity of metals by this device. Watch it now. Watch it. Look at that. Oh, that's terrific. That's terrific. Incredible. Now you watch the... Watch the frost gather. I'm coming back here. What did I put in here? I put in here another rubber ball. Notice, it was sort of elastic. Watch it. There it is, rubber ball. Now, where is that plate? Listen to the plate. I have to get my little mallet. Listen. You remember it was dead thud-like. Listen. Huh? I'm going to cool it some more. The strange properties. One thing more. I have here an electric lamp, as we call it, and I'm going to plug it into 110 volts. Watch. I'm going to plug it into 110 volts, and the lamp will light very feebly. There it is. I hope you can see it. Very feebly lighted. Now I have a coil, a wire coil in series with the lamp. I'm going to cool the coil. A long time ago, and another time later, I will show you that the electrical resistance of a conductor decreases with lower temperature. So, if I freeze this coil, watch the lamp. Watch the lamp. Is not the lamp getting brighter? The lamp is getting brighter. Brighter, brighter, brighter. Brighter and brighter. Look at the lead coil. Look at the lead coil. Look at the frost here, and this is a beautiful demonstration. Do you see the copper is frosted all the way, whereas the stainless steel is frosted only to here, which suggests that copper is a vastly better thermal conductor. Now, where am I? I like to look at that balloon again. Look at that. Look at that. It's a little cold on my hand. A little cold on my hand. Now, a tragedy to do. Here is that beautiful flower with which we opened the show, and I hate to abuse it in this way, but I want to show you the instantaneity with which this process of freezing takes place, which now has something to do with this new subject of cryonics, the freezing of human beings who have just now died in the hope of preserving the cadaver, the body, for future resuscitation when this is conceivably possible. Look how bright the lamp is now. Notice, very bright. The resistance of a conductor decreases. Watch the lamp now go dimmer. I'm going to immerse the rose in the liquid nitrogen. Watch it. Boiling vigorously. Boiling vigorously. Pretty soon, when it reaches the temperature of the liquid nitrogen, the system will cease boiling, and you'll see the dramatic effect that has taken place. One further thing, a little bell. Listen to the pitch. Now I'm going to freeze it. Notice it boiling? Watch the flower. There it is. A shameful thing really to do to so beautiful a living thing, but this is the consequence of very low temperatures. I want to try the lead plate again. Watch the lead plate. There is a ring. There is a ring to the lead plate. And as for those marshmallows, if I can get one out, watch it. There is the marshmallow. There it is. And now, what remains to be done? To point out to you that the lamp is dimmer now. Oh, my kettle is empty. And I can try one more pair. Here is aluminum and brass. Aluminum and brass. Let us see the results here. There it is. And we shall see the frost gather. And here is another ball. Watch it now. There it is. And finally, the balloon, whose volume is diminished nearly to zero, volume of gas. But the response to the thermal energy of my hand, very substantial and quick. And I say, the drama of low temperature stuff is something to be stirred by. And I thank you for listening.